on stage.
Great. Thank you, Nicholas, very much for having me. I regret that I haven't been able to participate more in FIPSAC this year other than by kind of bombing in to give this talk. Yeah, this is my first time even telecommuting to Israel. It's very nice. So in some ways, I should just say this is joint work. I mean, in all ways, this is joint work with my co-authors, Helen Jenny and Gautam Webb. They were my graduate students back in the day. And in some ways, this is a continuation of Helen's talk from last FIPSAC. So Helen was talking about the double dimer model and some work on enumeration of configurations in the tripartite double dimer model. We're going to use that that stuff heavily in this talk. So the summary is we're going to prove an identity that's coming from algebraic geometry. The identity relates to counts of plane partition-like objects, which I will call V and W. V really does count objects that are almost exactly like plane partitions, but with sort of, instead of being stacks of boxes in the corner of a room, the room has some baseboards now. So it's a slightly more intricate question than the plane partitions. The other box counting function is W. W is going to count a much more exotic object, but it'll have the same data, sort of three shapes of baseboard-like legs, and they're going to be related up to a factor of this. Can you see my cursor? Incidentally, I guess that's one thing I didn't check.
With a bit of lag, but yes, we see it. At least I see it.
Okay, so I should move slowly, but then it's fine. Yeah, so this here is McMahon's generating function for plane partitions. So where's this identity coming from? I haven't defined anything, so I'll do that in a later slide, but that was the main motivation for this work. So yeah, this identity, I would say, was conjectured in geometry. These two generating functions that I'm describing are essentially curve counting generating functions. They're going to count some kind of curves in a toric Calabi-Yau threefold, which is just some kind of complex three-dimensional space. Of course, to the geometers, curves are cut out by like ideals of polynomials, right? So these I'm going to be thinking of the ideals as monomial ideals. That's sort of why plane partitions are coming up. They're closely related to monomial ideals. In some very high level sense, these two curve counting theories are supposed to be equivalent. So we're supposed to have some kind of identity such as the one that I've shown. It's sort of a little bit difficult to say exactly what corollary we've proved in geometry, but we have proved a geometric fact. So what basically wound up happening is that the W generating function was only conjecturally the right generating function that counts these geometrical invariants of interest. The geometers proved by other means, this wall crossing technique that they have, that the corresponding geometric counts were actually the same. So what we did was directly prove the identity on the previous slide. And what that does is it proves that W is actually giving the counts that the geometers conjectured that it did 10 years ago. I should say, incidentally, DT is Donaldson-Thomas, PT is Pandera-Pandey-Thomas. I'm not going to get into any of the geometry. And in fact, you should really take this talk as being a talk about the dimer model. In the sort of embarrassing terminology of our times, I say I'm just counting things, and it was a very hard counting project for me. What we're going to do is we're going to relate these box counting problems that the geometers came up with, coming from counting ideals in their space, to the single and double dimer models, respectively, in the two theories. The single dimer model correspondence is going to be kind of a folklore correspondence. It's going to be one you've seen before. The double dimer model correspondence is deeply mysterious, and we would like to know more about it. And to me, it's the most interesting part of this model. Somehow it's a fancier generalization of the fact that rhombus tilings give you the same information as plane partitions. And somehow that's the thing that I want to emphasize in this particular talk to this particular audience. How do we prove the identity? Well, what we actually wind up doing is showing that these two quantities V and W satisfy the same recurrence. The recurrence is going to come from some kind of condensation identity in the two models. And I'll talk about what that means. A second interesting thing is that the recurrence that they both satisfy is not predicted by geometry. We found it by following our nose from the Daimer model. And it is much simpler than it has any right to be. And this is another mystery that I would like to understand. Okay, quick outline. First of all, I'm going to talk about the Daimer and double Daimer models as we use them for this project. I'm going to sketch the definitions of the box configurations. Of course, it's always a bad scene when you have to sketch a definition. No mathematician likes that, but it's intricate. And the way to understand the definitions, at least in the PT box configurations, is to step away and meditate upon them for a time. So, but let me try and give you some sense about what it is anyway that we're counting, and then I'll explain where this recurrence comes from that we solve. Okay, so let's start with the Daimer model. Daimer model is the statistical mechanics name for the study of perfect matchings on a planar bipartite graph. I guess I didn't write that down, but I've got a picture of such a perfect matching here on such a graph. For us, the graph we're going to study is always going to be some chunk of this honeycomb graph that covers the whole plane. If you'll recall from previous slides, the generating functions that I'm interested in have these parameters mu1, mu2, and mu3. So I don't know if I said it, but these are three Young diagrams. These are integer partitions. Integer partitions have this description as a Maya diagram, right? Sort of beads on a lattice that describes the shape of the boundary of the partition. And I'm pretty much always going to be taking a chunk of the hexagon lattice that's itself shaped like a bigger hexagon. And then I'm going to be removing, let's see, I wonder if I can just zoom annotate this. I'm going to be removing some of the vertices on the boundary of the hexagon here. And those vertices that I remove are going to sort of correspond to the Maya diagrams of these partitions, this bead representation. And similar down here, there's another bunch of dots taken out. Is a Maya diagram an abacus? Yeah, I think a Maya diagram is an abacus. I think that's right. I usually think of the abacus as having a bunch of, several strands, and that has something to do with the K quotient, but whatever. Another way, if you like Frobenius coordinates for partitions, you can also say that the locations of these removed vertices have to do with the Frobenius coordinates. Anyway, the Daimer model was studied by lots of people. I think perhaps initially by Castellan in 1961, statistical physicist. He was interested in, literally counting configurations of perfect matchings. One situation where this comes up, for what it's worth, is if you've got like a sheet of graphene, it's made of carbon molecules. We all know theoretically from chemistry that carbons like to form 4 bonds, but there's only 3 bonds in this graph. And so maybe the extra bond becomes a perfect matching. So there's reasons for the physicists to care about these things. What you care about is the graph gets a weight function, and then you put signs on the edges. And let me again indicate that we're working with a very simple graph here. In the particular case where all of the faces are hexagons in the graph, which is what I want, all of the signs are going to be +1. So I'm not going to talk about the signs anymore, but do know in general, you have to put signs on the graph to make the next thing I'm about to say work. So there is a matrix. Oh, I have to remove the annotation. Sorry, I've changed my tool chain slightly and nothing is working quite the way I expect. Yeah, so I've got this graph. It's got an adjacency matrix, as all graphs do. It is a bipartite graph. So that means I can put all the white vertices first and all the black vertices second, both in the rows and the columns. And then I get this back diagonal block matrix because there's no white vertices connected to other white vertices, right? It's all white vertices connected to black vertices. So the matrix that I'm talking about, this Castellan matrix, is just that chunk of the adjacency matrix with signs and also with weights on the edges. Very simple example here of just one hexagon. I've labeled the black vertices 1, 2, 3 and the white vertices 1, 2, 3. I've already forgotten what I've done. I think I put the white vertices in the rows and the black ones in the columns. And then there's weights on the edges. So I've basically made all the edges weight 1 if they don't have anything written on them. So that's a weight 1 edge. The only weight not 1 edge is this edge here with a Q on it. All of our weights are going to be monomials in Q. And so this is the Castellan matrix. After you write down all of those plus signs in it, you can see 2 entries in each row, 2 entries in each column, corresponding to the fact that this is a cycle. The determinant of this matrix winds up being minus 1 plus Q. And in general, the determinant of this thing is going to be a signed sum of perfect matchings. When you think about just expanding it out over like the usual recursive Laplace expansion thing, where you write the determinant as a sum over sort of like the permutation matrix pieces that appear in the determinant. Every such thing is a perfect matching, and you just have to rig it so that they all appear with the positive sign. This is always possible for a planar graph. That was Castellan's theory. In this case, the perfect matchings are weights 1 and Q. Here's the weight 1 perfect matching on this hexagon graph, and here's the weight Q one. Notice that this is also the same as the counts for the number of ways to put one box in a room. Either you can do it or not. If you don't put a box in the room, the configuration is weight 1. And if you do put a box in the room, that configuration is weight Q. So this is actually computing the generating function for some very simple plane partition problem. Plane partitions in a 1 by 1 by 1 box. Okay. So let's see here. Let me just close my annotation. Can I even close my annotations? I don't know. Okay. Oh, there we go. Let me just throw this off the screen. Hopefully you can see more of my slides now. So that's one of the Deimer model type things that we want to study. The other one is the tripartite double Deimer model. Okay, so a colleague pointed out to me that my slides are pretty bad for colorblind people, so I apologize for that. What we have here on the same sort of picture, so this is a hexagon graph. There are special vertices called nodes around the edges. Nodes come in 3 colors, red, green, and blue. And what I've done is I've superimposed 2 perfect matchings. One is a perfect matching on the graph with all of the nodes. And I think for those that can see it, that is the red perfect matching here. So if you just ignore all the black edges in this picture, you see a red perfect matching. The other perfect matching is going to be a one on the graph with the nodes gone. Okay, so if you delete all of those colored or circled nodes around the edges, that's the black perfect matching, or the other edges. Some of the edges appear in both matchings. In this particular configuration, you know, what you get when you do that is you get a bunch of paths, when you think about it, connecting the nodes in various ways. You can also have these doubled edges. And then another thing that can happen, but I neglected to show here, is you can have closed loops appearing in this perfect matching. Much as before, I have this partition data that I'm going to be using in my application to geometry, mu1, mu2, and mu3. They're going to encode what vertices are not nodes. So here is a non-node right here, for instance, and here's another one, just in the same abacus or Maya diagram way. Okay, so the summary from FIPSAC 2020 is that Kenyon and Wilson, in I think it was 96, 97, and later Helen Jenny both wrote down matrices whose determinants count these tripartite double dimer configurations. I said a word I didn't use before, so I'm going to go back to this slide. Tripartite means what it means in graphs, but here I'm just sort of thinking of the connectivity between the nodes. I'd ignore the fine details of the matching. You'll see that this green node is just kind of trace it along here. It's going to be connected up with this red node. Tripartite just means that there's no two green nodes connected in this way, no two red nodes connected, no two blue nodes connected, just as for a tripartite graph. And in fact, there's only really one possible sort of connectivity if I fix the node numbers. It's these sort of three rainbows of arcs here, and that's what we're seeing here. Yeah, so Helen has this matrix whose determinants count such configurations. The size of the matrix is basically like, you know, it connects half of the nodes to the other half of the nodes. So it's a square matrix, and the size is the size of half the node set. Kenyon and Wilson have a similar, somewhat more complicated matrix that's easier to prove things about. The advantage with Jenny's matrix, which I will call J for Jenny, is that its minors are also meaningful. So if you take minors of this configuration, that's going to correspond to turning some of the nodes on and off, making them not be nodes. So we're gonna need that fact heavily in the sequel. Okay, so I talked about these two counting problems on perfect matchings. Now let me talk about the box counting plane partition type problems that I'm going to use them to study. Yeah, so these are basically going to be some special kinds of modules, C, X1, X2, X3 modules. So, and that's sort of where the weird structure is coming from. This is just a combinatorialization of some way to talk about certain monomial ideals. They're all going to be subsets of the integer lattice, all of these box configurations. And I want you to think of the integer lattice as being a tiling of 3 space by cubes. There's going to be one cube at the origin. That's the 0, 0, 0 cube and so on. Okay, so first of all, there's these 3 cylinders. So remember, I have these 3 fixed Young diagrams that are part of the data of my problem. Imagine putting, let's just think about mu1. So I guess, yeah, so put mu1 in the YZ plane, its Young diagram, right? And then extrude it in both directions along the x-axis. I have an infinite cylinder that is the sort of with mu1 as its cross section. It's got a part in the positive orthant called the positive cylinder, cylinder 1, and then it's got a part in the negative, one of the negative orthants, cyl 1 minus. And similarly, there's cylinder 2 up the y-axis, cylinder 3 down the z-axis. These cylinders are going to meet in a somewhat complicated way in the first orthant, which I've shown here. This picture shows the negative parts of the cylinders as well as their intersection. It's possible for the cylinders to meet 2 at a time, such as this purple region. This purple region here is not in the yellow cylinder, but it does happen to be in the blue and red cylinders. And it's also possible, to have other such things. So this green cylinder here, I guess that's not in the that's not in this red region. And there's also possible to have 3-fold intersections of the cylinders. So let's just use a Roman numeral 2 and a Roman numeral 3 to describe the locations of these intersections. So first box counting problem, it's the Donaldson-Thomas problem, which I said was very similar to plane partitions. So what we're going to do is we're going to stack cubes in the first octant, where all the coordinates are positive. We're going to put them on top of the cylinder condition, the cylinder configuration. So there's these 3 baseboards. I think I described them earlier with cross-sectional shapes of 3 arbitrary partitions. And I'm just going to count the number of ways to add boxes to this baseboard type configuration. Each one of those is going to be a configuration I got to count up. Simple example, in the case where the partitions are all the empty partition, which is allowable, what I'm doing is literally just the plane partition problem, which McMahon solved in, I think, in the early 1900s. The other much more exotic box stacking problem is coming from this other geometric theory, PT theory. my boxes are going to go inside the negative parts of the cylinders and also into the region where the cylinders intersect in the first octant. So yeah, imagine just taking these negative cylinders that are going out to the back and down through the floor, together with this somewhat complicated region where all three cylinders meet. I'm going to put boxes into there. Gravity's going to pull them up and out of the box, more or less. And moreover, boxes in the threefold intersection region are going to come with labels. They're either going to have a label, which is, think of it as like an arrow pointing, really an element of complex P1, but just think of it as a direction that I'm pointing. And if they don't have a label, that box can appear with multiplicity 2. So it's actually possible to have two boxes in one spot. This is all, of course, there is very weird constraints on what the labels are, but basically they have to be the same label if two boxes are next to one another. And there are other constraints imposed by the presence or absence of other boxes in the cylinders or in the twofold intersection region. I think this is the part where I sketch the definition, right? It's just very intricate, and I don't think this is the right format to go into what it is. Fortunately, there's a better way to describe everything, and the better way is with the Deimer model. So this is sort of like the first miracle that I want to kind of understand. There's this sort of well-known folklore correspondence that relates a plane partition or a related object to a lozenge tiling. You just close one eye, forget perspective, and you see that you have a lozenge tiling of the plane. I can I can decorate each one of these lozenges with a perfect matched edge and then not draw the lozenges. And so I get a Deimer configuration. And the one thing to check is that this is just a patch of it. This perfect matching covers the entire plane. So notice again, you see the abacus coordinates of these other partitions showing up around the edges here of my graph. A similar thing happens in this more intricate PT theory. There's a way to take that stack of boxes and pull it apart into two pieces. There's one sort of plane partition-like piece that corresponds to the sum of the boxes in the first orthant. And then there's another sort of weirder looking Y-shaped piece that corresponds to any boxes that actually got piled into those infinite cylinders. And you do the same sort of folklore technique, giving a perfect matching corresponding to the positive orthant boxes, more or less, and then a perfect matching corresponding to the other stuff. And then you superimpose those two perfect matchings to get a double Deimer model. Now, the reason that I was somewhat content to just sketch the definition of what it is I'm even counting is that these intricate labeling rules that I was coming from the structure of this CX1, X2, X3 module in geometry exactly turn out to imply that the double Deimer model that I thus construct is tripartite, that it has this rainbow shape. You'll see that all of the arcs here are going in a rainbow. All of the arcs over here are going sort of rainbow shape and then rainbow shape again. There's no arcs coming from one leg and going into the other leg. So that's the first mystery, in some sense, what I really want to understand. Now let's talk about what the generating functions are. They're just they're just weighted counts, and as I suggested, the generating function for the boxes can come from the weighted generating function for the Deimer model. So the geometers want a certain very specific normalization for this generating function. They want it so that they want to make it a sort of formal Laurent series, so that the first few terms are negative, but that's sort of convention. It doesn't matter too much. So V, the one for Donaldson-Thomas theory, the plane partition one, is literally just the generating function for plane partitions with these cylinders removed. The other one is a little bit more intricate. Again, not too surprisingly, there is a multiplicative power of 2 that shows up corresponding to the labeling. Oh, I see I'm nearly out of time. Let me just assert that it's complicated, but not too difficult to compute. Unfortunately, skip through the example. And let me just say that the recurrences that constrain these things are coming from condensation of these two determinants. So this is Dodgson condensation. There is a relation that happens in any determinant that comes from deleting rows and columns as minors of the matrix, and it's this three-term quadratic relation. So you just apply this recurrence to the Castellan matrix and to the Jenny matrix, and then you find that that's, it just sort of looks like this. It corresponds to perturbing the partitions mu and nu. And again, there's just a couple of very simple constants that show up in the recurrence. I have no reason why they should be so simple. Again, following that example through in the past. And the last thing I'll say, it is clear that you will get a recurrence that describes both these dt and pt generating functions. It is not at all clear to me why the same recurrence comes up in the two models. You'll get something that looks kind of like condensation, but it seems to be some kind of miracle that you actually get the same recurrence. We don't know what it is. It's not coming from geometry. It's just exactly coming from condensation. And for future work, we would like to explore any other instance of this relation between the single and double dimer models. Somehow it's deeply mysterious to me that these theories are connected in this way at all. They seem very different. Thank you very much.
Thank you. So, questions?
I have a couple of questions.
Is that Dan?
The first one is kind of obvious. Is there a bijection between, you have these topological vertices on one side and plane partitions and triple, whatever, trimers on the other side?
Yeah.
Is there a bijection where you have a, you take a topological vertex, maybe you do some RSK type stuff and out pops the plane partition and a trimer? Or
right, that would be awesome, right? That's our proof is very badly non-bijective. On the other hand, and if I were sort of looking, there's in the case where one of the plane partitions is, there's these parameters lambda or mu1, mu2, mu3. In the case where two of them are empty and there's just one partition, then as you say, I think you can do some RSK stuff and come up with a bijective proof of the identity that I've shown. Like you can kind of even imagine what it would look like, right?
RSK.
This identity here. We're sort of working on that. There's a way to write it down carefully with toggles, we think. I've given that to a current graduate student, and we'll see what comes of it. In general, I don't even know how to prove. The only thing I know how to do is what I've shown you. The condensation identity that. Let me comment. Yeah, so condensation can be bijective also, right? There's this beautiful proof of Eric Kuo that graphical condensation works for the single dimer model. Jenny's proof of the same condensation identity in the double dimer model is again very badly non-bijective. It's coming literally from these linear algebra techniques applied to her matrix. So I would very much be interested in any way of doing anything bijective with any of this.
All right, thank you. We still have time for one question from someone else, maybe?
Nice talk. Have you thought at all about boxed versions of these generating functions?
So
finite sums?
Yeah, understood. So that is not natural for the geometers. So, this has been a very long running project for me. I started even thinking about this close to a decade ago. It was so long ago that when we published the paper, I had to include one of my postdocs as a grant that supported the research. I'm associate professor now. There are a couple of other problems, again, sort of infinite, coming from geometry, where the double dimer model is closely related to the single dimer model, but is coming from like a totally different part of geometry that does this. And there are, I think, so yeah, better answer. Greg Musiker and Helen Jenny and Tri Lai I forget the status of the paper, but they're working on a sort of a cluster algebras application of this, in which the double dimer model arises in cluster algebras. And their graphs are finite. So it's much more like the box version. But does this work for box plane partitions on the nose? I kind of think not, but the geometry somehow really wants the containers to be infinite.
All right, thank you very much. It's been a relatively long session, so I'm going to officially close it now, but I do recommend to everyone who wants to keep chatting and do more math and discuss to stay around. Thanks a lot to all the speakers. It was great to see people from all over the world joining. Enjoy your evening, day, or whatever it is for you. And I hope to see you very, very soon at this or some later PeepSac. Bye-bye.
Bye. Oh, and before you leave, don't forget there's a poster session in a few hours, especially for the American audience.
Yep. Thank you, Dan, for reminding us.